All right, everybody, welcome. We're just waiting a little bit for, all of the attendees to come in. My name is Justin, and today speaking on control instruments is Yvette from ESD. Before we begin, I was hoping, if you don't mind, to take a quick 30-second poll, just talking about your role in the industry and how long you have been how long have you been at that role? So if you are willing to do this, I'm going to launch the poll right now. Let me know if you are having trouble opening or seeing this. Shouldn't take too long. And all right, just wait another 5 minutes. All right. All right, well, thank you everybody for participating. Again, welcome to the first of 4 webinars for the YEA Astronomy Spring Conference. Today, we're talking about control instruments. Our speaker is Yvette from ESD. She's going to be talking to you and talking about the subject for the next 45 minutes. If you guys have any questions during the presentation, please refer to the Q&A tab on the bottom of your screen, and we'll answer that as we will answer that either during the presentation or after, depending on the question. All right, Yvette, if you don't mind taking it away.
Yep. Hey everyone, I'm Yvette. As Justin said, I am here on behalf of Environmental Systems Design, ESD. I've been at ESD for almost 3 years, and I'm here with my peer, Monique Lindquist. Do you want to briefly introduce yourself?
Hi, I'm Monique Lindquist. I've been with ESD 2 years. I've been in the industry about 15 years doing consulting engineering and also as a contractor working primarily in the controls industry.
Yeah, so I started off my career in controls as well. Did a brief stint in commissioning, but back in controls, and I'm here to present on controls instrumentation. So let's go ahead and get started. So today's agenda is to discuss instrumentation and controls devices, which can be either Division 23 or 25 when following AIA specifications. We're going to break down our typical specifications and the sections that are involved in that. And then we'll get into like a high level overview of sensors, actuators, which are applicable to the control of dampers and valves, airflow monitoring, and water flow meters. And I just want to say that there are numerous technologies and we can't possibly cover all of them today. So we're just going to get into a few of them. So to break down of our typical specs, you'll have like the general section, which again is just like the summary submittals that we expect from our BMS contractors. And then like the maintenance material submittals, just like providing those additional spare parts for our customers. And then you get into the nuts and bolts of the specification, which is the products, and that's kind of digs deep into the types of products that we're specifying per project and what we want the BMS, what we want to see from the BMS contractor provide for our various projects. And again, it's just like a small breadth of devices that we may specify, which includes like humidity sensors, temp sensors, carbon monoxide, carbon dioxide, DP for air, DP for water, flow meters for air and water, BTU meters, oxygen efficiency, and the list goes on. And then lastly, you'll get into the execution portion, which again, like just what we're expecting of our contractors in terms of providing these products for our projects. So what is instrumentation? Well, if you go into our just Webster Dictionary of Instrumentation, it is that instrumentation is the use or application of instruments as far as for observation, measurement, and control. So, I mean, this is just like a really old depiction of like controls, but basically it's kind of using instruments to observe and see what's going on presently, and then the reaction of the system according to that. And to go a little bit further into that, just you want to go into like the cause and effect, basically, is kind of how you'll see what instrumentation is and like why it's necessary. All of these instruments are reacting to changes in temperature, humidity, or other day-to-day changes. It all boils down to this cause and effect, kind of like this simple thermostat. You know, whether there's a rise or fall in temperature in a space, you can have dampers open, fans turn on, and valves open for cooling and heating. And then when the space meets a set point, that space again reacts and starts like closing various dampers, fan or valves, and turning off fans. So that was just like a simple explanation of, you know, instrumentation. So then we can get further into the weeds of what are sensors and devices. So most of us are familiar with like temperature sensing devices. Most of our temperature sensors are resistive element type of sensors. There are many different types of temperature sensors that we could see, and it's all kind of comprised of this same technology. You've got that resistive tip on the sensor that senses the temperature and changes the resistance value on the wire back to the BMS system. So just like some examples, this would be like a duct mounted temperature sensor, temperature sensor with that bulb sensing the temperature at the end here, and then sending that resistive element back into the BMS system. You've got an immersion type temperature sensor, which you would put into like a piping system, and it's measuring the temperature of whatever media may be in there, whether it's water, glycol, or another media. You've got kind of like just a typical room temperature sensor where the air is like flowing through this device, again, touching like a sort of bulb in that device and then going back to your BMS system. And then you also got like wall style sensors. And then as you can see here, we've got ones with digital displays, without digital displays. It all kind of depends on what your client is asking for. Some clients may not want their tenants to be able to see the current temperature in the space, as people may want it to be warmer or cooler and cause a back and forth when controlling the space. Some clients may want sensors with overrides of like plus or minus 1 degree, for example, in the space, so that the tenant in the space can override that and turn on the terminal unit in that space to get more primary air. Some of these sensors may also be combination sensors. So in addition to the temperature sensing element, they'd have like a CO2 or humidity combination, which would be tied to the terminal unit in the space, and can also cause an override to the control to pull in more fresh air into the space, regardless of the current temperature, as a reaction to increased CO2 in the space. So we've got to put in that specific detail in our specifications to ensure that our clients get what they want or what they need due to code in that space. So just to reiterate that. And then lastly, we've got, averaging sensors. Those would typically be used in a space where there's like low airflow or stratification. So in a position such as in front of a coil. You also have the averaging sensor, which would be attached to a safety device such as a freeze-stat, so that when it senses like very low temperature in whether it's like at the bottom of the duct, because typically the cold air falls, it would initiate that safety sequence to avoid freezing your coil. So to continue on the conversation of sensors, we've got also various like gas measuring devices for refrigerant leaks, which can be in like electrical rooms, or carbon monoxide and carbon dioxide sensing, which can be used in garages, labs, educational spaces, or conference rooms, and many other locations. And the readings of these devices can then trigger the opening of dampers in the space, or the turning on of exhaust and supply fans. Lastly, we've also got pressure sensors, which you'd want to use for water or air side systems, and can be used as like a set point to control your pumps or your fan motor speeds. And that was just, again, a breadth of the various types of sensors that you could possibly use in your systems. So next week, we'll get into control dampers and actuators. We'll get a general overview of blade patterns and blade types, and the application for indoor and outdoor. And then we'll get into the actual controlling mechanism of those dampers, which is the actuators. So in terms of blade patterns, you've got parallel, opposed, or round. When considering a blade pattern application, you want to think about the relationship between airflow rate and the position of the blades. So for opposed blades, when you first open the blades on that damper, the relationship between the airflow rate and the position shows a nonlinear relationship. But as you start to open up that damper more, the relationship starts to become more linear and controlled. So this blade pattern would be best for like a throttling application and controlling air volume, thus more like appropriate for modulating applications. For parallel blades, when you first open them, they have a very steep, more aggressive flow rate to damper position curve. So there's a significant change in the flow rate when you're going from a closed to open position. And thus those would be best used for a two-position kind of isolation damper application. And then lastly, you've got your round dampers, which you'll use to control CFM. And typically you see those in terminal unit applications such as VAVs. And so then getting into blade types. So you have two types really, like the airfoil blade profile and then this like triple V blade profile. So in terms of that airfoil shape, it's shaped more like an airplane wing, and this blade is kind of more preferred since they have a lower pressure drop across the damper opening due to that more aerodynamic shape of the blade. So overall, we tend to prefer that blade shape in our applications. And then in terms of actual blade types for the dampers, you've got low leakage, insulated, thermally broken. So for that, low leakage airfoil damper, typically you kind of just have your aluminum and cap blades. And then if you go into like the next step up, which should be like the insulated blades, those blades are constructed with that same aluminum shell, but they're injected with a polyurethane foam, which would help in terms of isolation and just that insulation. So you'd want to use this in more of a like coil freeze up concern, such as in air handling units. And then the next step up above that is the thermally broken kind of blade, which again is that same insulated blade type, but in addition to just the blade being insulated, the frame is also insulated. And so the blade, the frame is thermally broken with that polyurethane resin along the frame. And then so in terms of whether it's like best application for indoor or outdoor, you'd want to use that insulated frame where coil freeze up is a concern. So like in your air handling unit, you want to use it for that where the blade is having an outdoor application, such as the exhaust fan or the outdoor air, or the exhaust duct and the outdoor air duct, just to avoid the cold air going through that space. And then for the indoor application, you would want to use this like low leakage dampers for your return air duct or your supply air duct, where it's not a concern for coil freeze up. Okay, so then getting into your actuators. Typically your actuators are furnished separately from your dampers and valves. So it would be up to your mechanical contractor to install that damper or valve, and the BMS contractor would then install your actuator to control the damper and valve. As stated previously, you do want to choose your dampers based on the best application for control. And you also want to have those considerations for the type of valves that you're using in a control setting, but we won't be touching on valves today. So the industry standard for actuators is an electronic actuator utilizing a microprocessor controlled brushless DC motor. And when deciding between two position or modulating, you want the two position for isolation purposes and modulating to throttle air or water flow. And then there's also this third type of modulating, which is called a floating signal. And in that case, you'd have two control signals of a 24-volt AC output, and they're sent as pulses to start opening up the damper. And those like little pulses are sent slowly and like modulate that damper open, or those pulses are then slowly sent again to slowly modulate that damper closed. This isn't the preferred control for dampers in an air handling unit setting, but you can see those more in a terminal unit setting, such as a VAV application. And then in terms of the signals used for these actuators, just previously the controls industry used pneumatic controls or that pressure control, which is why you'd see that PSI signal. Nowadays, you're using volts or amps. For modulating signals, that signal can range from 2 to 10 volts or 4 to 20 milliamps. And these values are important in terms of how you want to see your system react to those specific values. So you'd want to see your damper be closed at a 2-volt signal, and then be at like minimum, for an example, for an outdoor air damper example, you'd want it to be at minimum OA at a 6-volt signal, and then it would be fully open at a 10-volt signal. And then a last thing to consider for actuators is setting a fail position. So you can set your actuator to fail in a certain position when there's a loss of power. And so you'd provide that actuator with a spring return so that in the loss of the power condition, the actuator would fail your damper or valve in a certain position, whether it's open or closed. You'd want to fail your damper open or fail your damper or valve open when there's a safety issue as a concern. So for example, in an air handling unit situation, you'd want to prevent your coils from freezing. So you'd fail those outdoor dampers closed. Or for example, in the supply duct of that same air handling unit, you'd want to fail your dampers open so that there's no overpressurization of the duct. And then lastly, you'd want to fail in last position when there's not a concern for the safety, such as like in a terminal unit, such as a VAV damper. So next I want to touch on airflow measuring devices. And I'm going to highlight two major types of airflow measuring devices. One being called thermal dispersion airflow measuring, and the other differential pressure. So just giving a rundown of these examples provided here, we've got the thermal dispersion types up top here. We've got like a pitot tube kind of layout here. And then this bottom right is a piezometer ring airflow measuring device. So these two you'd be using as the thermal dispersion. And then these bottom ones would be using that differential pressure. But we'll get into what those mean next. So digging into thermal dispersion, which you may also know as hot air anemometer. So in this lower left-hand side picture, we're depicting this temperature sensor element right here, which is serving as like our reference temperature. And then you've got this like heating element a little distance away to the left. And the device is keeping a constant delta T in between those two devices. And then depending on how fast the media, which is flowing through this device, is flowing, it requires more or less current to keep that delta T constant. And then so that current is kind of directly proportional to the flow of the media. And I say media because like this technology can be used for gases, like many types of gases, but you know, in our case, we're using it for like airflow rate. And so this is like the main principle of thermal dispersion and like how it's used in these devices. We don't really need to dig deeper in terms of understanding how this works, but just wanted to give a little bit more explanation of this type of device. So to the right, you're seeing two applications of thermal dispersion. This would be like a duct mounted application. And then this is this like ring would be at the fan inlet, which I want to emphasize that it's always going to be placed on the inlet of a fan because there's more laminar airflow, whereas downstream there would be more turbulent airflow and not a great position for measuring that airflow. And then lastly, I want to go into like the pros and cons, or the pros of this device, which is that with a thermal dispersion device, there's less orifices compared to, say, the pitot tube, which minimizes that clogging from dust. And so then going into our next application, we've got differential pressure. And so we have this like piezometer ring, which we'd likely see at the inlet of the fan, you know, as compared to like the other ring that we saw for the thermal dispersion application. And then we've also got the pitot tube application here. In terms of the piezometer ring, it's using the Venturi principle to do this measuring of airflow rate. So there's a sensor located at the outer edge of the ring, and then that's measuring the pressure at that outer edge. And then there's an additional sensor at the inner ring, also measuring that pressure. And so the difference between those two pressures, and then using the Venturi equation, which I don't have written here because we don't have to do the math, the device is doing it for us. It calculates the airflow going through this device. And then in terms of the pitot tube application, it's got this like honeycomb layout here that you can see. And it's, and that we're using that honeycomb layout to keep the airflow like laminar through the device. And then so the pitot tubes are located inside this device, and they're measuring the total pressure, which is upstream on the upstream side of the airflow, and the static pressure on the downstream side. And the difference between those pressures gives you the velocity pressure, which is directly proportional to the airflow. And then, as I explained before, the cons of this device is like this honeycomb layout, because it kind of acts as a filter and collects a lot of dust and requires a lot more maintenance, and could fail due to that lack of cleaning. And so the last topic I want to cover is flow meters. And there are many types of applications of flow meters as well, and we've only selected 5 of the more prominent types to cover today. So the first kind of flow meter is a turbine flow meter, and there are many reasons why they're great, and then reasons why you may not want to select them. So this is an insertion type, which means that it can be hot tapped. So you don't necessarily need to shut down your system if you have an existing system to install this type of flow meter. They're incredibly accurate and inexpensive compared to other styles. A reason you might not want to choose this meter is because it has moving parts. The rotor has to rotate on bearings, and those can get worn out. Over time, the meter will become less accurate and unusable. So it's important that when using this device, you have very clean water, and to make sure you're using a media similar to water, not a media that like could be too viscous. Otherwise, the meter won't work. And then you also need a certain length of straight pipe upstream and downstream of the installation of this meter to ensure smooth flow through it. And then again, lastly, anything that's inserted into your pipe system will have a pressure drop. So as we touched a bit on this device, it works with like the rotational parts. So as the water flows, it starts to rotate these rotors here, and the rotational energy creates pulses that are then measured, and the transmitter processes the signal pulses to determine the flow rate. So contrary to the turbine style is the electromagnetic insertion flow meter. If you were to say that you don't want the turbine style because you don't want moving parts, but you still want an insertion type, then this sensor would be the way to go. It's still an insertion type. So again, so you can do that hot tapping, as we said before. You don't have to worry about the moving parts with this one. You don't need quite as much length of pipe for installation, since you don't need to control the flow as steadily to get an accurate measurement. And it's also a comparable price. It is slightly less accurate than other models and the turbine style, but if you did some research on like different manufacturers with different price points, that might create for more comparable accuracy. So it's kind of cool to learn a little bit of history in terms of like how these things work. So the electromagnetic insertion is thanks to Michael Faraday. He was a scientist in England in the 1800s, and it was through his invention that we learned that voltage generated is proportional to the movement of flowing liquid. So that's what kind of makes the electric magnetic sensor work. And then in his lifetime, he just had like a bunch of really cool things. And these are just two of his best quotes. So be sure to check him out just because he was a really cool guy. So then going into, using what he learned and how it works with this device. So we were talking about how voltage is proportional to the movement of flow. And then what is happening is that in this device, it generates a magnetic field within the liquid. And as the flow rate increases, the voltage signal increases. And electrodes located on the pipe walls read that voltage and process that signal into a flow rate. And so next we have the electromagnetic inline sensor. So this is, as opposed to the insertion meters, this is an inline meter. These are a bit bigger, more accurate, a more like fancy version of the electromagnetic insertion style. There are no moving parts, they're durable and have extremely high accuracy and very minimal pressure drop. They do, however, need a larger section of pipe and can be expensive. So if you're in the predicament that you don't have pipe that you can cut into or penetrate, and you're looking for a flow meter that doesn't do that, you can use this ultrasonic flow meter. They tend to be used on smaller pipes or pipes that you can't cut into. Some are clamp-on style, and they have inline versions available. These send an ultrasonic wave to measure the water flow, and they're moderately accurate and moderately expensive. So the way that these work is that there are two transducers located upstream and downstream of the pipe, and it sends ultrasonic waves through the fluid. It's measuring the amount of time that it takes to go from one transducer to the other. So if there was no flow going through this pipe, the time that would take to go from the transducer upstream to downstream and downstream back to upstream would take the same amount of time. But if there is flow, then there's a difference in the duration of those signals going back and forth. And the device is processing that difference in the duration and determining the flow rate from that. I won't dig deeper into the explanation of ultrasonic waves, but feel free to dig deeper to get a better understanding of how that works. And so lastly, we've got Vortex flow meters, which are primarily used for steam. So we've got another cool scientist, Theodore von Karman, and the way that these meters work is based on the von Karman effect. He discovered that the repeating pattern of swirling vortices is generated when flow passes through like a bluff body, which I'll explain further in the next slide. And another just overall great quote from him is that scientists discover the world that exists and engineers create the world that never was. So I thought that was a really good quote that I could add into here, especially since we're all engineers and discovering new things on a daily basis. And so then just going into how the von Karman effect works in this device. So there's a shutter, which is an obstruction in the flow path of the bluff body, and the shutter creates vortices when the fluid separates and forms areas of alternating pressure, differential pressure, and the transmitter can calculate the flow rate through the frequency of these differential pressures. And then I just want to reiterate that steam in itself is a whole animal, and meters don't compensate for change in pressure in steam, and pressure matters a lot in terms of steam. So that system would typically require additional pressure meters in addition to just like these flow meters. And so I think it's my last slide. Okay, so in terms of tying this all together, actually I'll just go back here. I just want to say that when you're specifying flow meters, you want to choose like your type of flow meter, the accuracy that you need, any special NICE requirements. If you need a NICE certificate, you can state that in your specifications. You want to state what range or what level of turn down should be achievable. And then if you need to specify how much pipe for upstream or downstream of straight pipe that you have available, you want to state that in your specifications so that you don't get a meter that requires much more pipe than you have available. And then lastly, I just want to touch on how all these moving parts and pieces tie together. Going back to that initial slide I showed you, it just all boils down to that cause and effect. And we need these various devices to be sensing changes in spaces, changes in the outdoor temperature or humidity or so be it, and your day-to-day changes. And that then triggers a response from your system of opening and closing things, turning fans on and off. And all of this works together in order to achieve the conditions that we need met, which is why controls is such a vital part of design considerations. So that's all I had to share with you all today. I believe we did have a question, maybe. Looks like it got answered.
We have one event.
Okay.
Question is, do you perform M&V data collection of the baseline and then following retrofits to determine energy savings? So it's not something that we at ESD have in our specs just as a required for all retrofits. A lot of it is because it depends on what you're using that M&V data for. If you're working with your utility, at least my local public utility, they're taking baseline energy data rolling back that they've collected, and they are actually just looking at the system as a whole and making assumptions on total savings on either electric or gas and rebating based on that. I have run into energy service providers and energy services groups that have performance contracts and are guaranteeing savings, and they have a very strict M&V process that they follow to ensure they're meeting those metrics of the contract. And doing all of that, the only caution would be if you need old data, make sure you pull that old data before you start disassembling a building automation system. A lot of BMS systems aren't holding data for all that long, depending on the customer and the size of the site. And so, yeah, you could risk, for instance, losing chilled water data from last summer as soon as you start the chilled water plant up for this summer.
It looks like we've got another question. I'll go ahead and ask Monique. Where does an anemometer fit into the different flow measuring devices you've mentioned? Or is it a separate type of measuring device used for measuring airflow only? I've only seen an anemometer before for measuring velocity of airflow in a duct.
Yeah, I've seen them for the same thing, measuring velocity in a duct. It's not something that you're going to see often. It's wind speed and wind direction. So you might see it on a weather station. You're not going to generally find it on an airflow measuring station.
Next question, is there a tool or resource you would recommend that could aid in selecting and sizing a water or gas meter for a specific application?
That's a good one. I would rate at that point, you're going to go product specific, which we'll stay out of, but I would go and look for your preferred product. The problem you're going to run into is it's generally pipe diameters up and down. So they're they're actually looking at flow and also pipe size. And then the big thing you run into when selecting a type is how much straight pipe can you find to install that meter. So one of the benefits of not the turbine meter is they actually need less straight pipe. The Vortex flow meters, the flow meters that you saw in the photos earlier, those can need larger runs of straight pipe. So it's all just going to be dependent on the meter type, and each manufacturer is also different as well as to how many diameters of straight pipe upstream and downstream are required.
I believe that's all our questions. Justin, do you have any wrap up things that you want to cover? I know we had like a post poll.